Hi guys, it's Mrs. Millison. Okay, one little part of conditional probability that I want to talk about is the at least one scenario. Okay, now what I did was I gave you a little, or there's a little formula the book talked about, 1 minus the probability of none raised to the power of the number of situations. Okay, but I want to show you where this comes from. This comes from a tree. Okay, so researchers show that approximately 78% of people like chicken. So if we randomly select 3 people, what's the probability that at least one of those 3 people like chicken? Okay, so the probability that somebody likes, oh, I could spell chicken right, likes chicken is 0.78. So the probability they don't like chicken is 0.22. Okay, so if I follow this, I would do 1 minus the probability of not liking chicken raised to the 3rd power because it's 3 people. So 1 minus 0.22 to the 3rd power. And that is something, I don't have the answer. Oh my goodness, I forgot to calculate that. 1 minus 0.22 to the 3rd power. So it's 0.989. Okay, so there is a pretty much a 99% chance that in 3 people, at least one of them is going to like chicken, given the fact that 78% of people like chicken. Okay, so where does this come from? Okay, it comes from a tree. We're going to have three extensions of our tree, 1 for each person. Okay, now people are independent. If I like chicken, that has no impact on whether you like chicken or the 3rd person likes chicken. Okay, so the probability of liking chicken is going to be 78% on every single branch. Okay, people are independent. Okay, plus we're from a population of so many people that the change in probability would be nominal anyway. All right, so here's my lovely tree that I already created. So here's the first person. They're either going to like chicken or they're not going to like chicken. So there's a 78% chance they're going to like chicken, 22% chance they will not like chicken. Okay, so that's the probability of event A. Second person, if the first person likes chicken, then I have the second person liking chicken and not liking chicken. The first person didn't like chicken, I still have the second person liking chicken and not liking chicken. Again, the probabilities haven't changed. Okay, so that's the probability of the second event. Third person is going to be off of every possible combination of the first 2 people liking chicken. Okay, so this is the tree that represents 3 people and whether they like chicken or not. Okay, so you'll see this branch are all yeses. All 3 people like chicken. There's about a 47% chance that all 3 are going to like chicken. What about the first 2 liking chicken and the 3rd person not liking chicken? About 13% chance. Okay, so we can go down each of these branches and see the combinations of people that like chicken and people that don't like chicken. So this one had 1 person that liked chicken and 2 people that didn't like chicken. That's only like a 4% chance. Okay, that's not going to happen. Well, it could. And then here we have the 1 person not liking chicken, but these are the 2 people liking chicken. Back to 13%. Okay, so where this at least 1 person liking chicken is basically every single branch has at least 1 person that likes chicken, except the last branch. This last branch, nobody likes chicken. Okay, so that's why, so this is why we do the probability of not raised to that power. So 0.22 to the 3rd power. Now, why do I subtract it? Here it is. Why do I subtract it from 1? Because remember, the addition of all the probabilities of all the possible outcomes equals 1. Okay, so if I take 1 and subtract the none to the 3rd power, I'm left with all these probabilities. So all these probabilities added up is the probability that at least 1 person will like chicken. Okay, so Mrs. Millison, couldn't I just draw a tree every single time and add these up? Yeah, I guess if you wanted to, but what if I had asked you about 25 people liking chicken and at least 1 person, out of 25 people, at least 1 person liking chicken? That's going to be a heck of a tree. I don't like drawing trees past 3 events because it just gets too busy. So that's why knowing this little shortcut is very helpful. Okay, so again, it all stems from a tree. Okay, just a little side note. we have our 3 different events, person 1, person 2, person 3, and the probability of the ands, we just multiply them all through. And they are independent, so that's that little formula. Okay, let's do an example with a table. Okay, and sorry, I typed that wrong, so I just handwrote it because I don't feel like typing it. All right, so let's say we look at a table. This is the probability of the number of pets somebody's going to have. 0 pet, 1 pet, 2 pets, or 3 or more pets. Okay, what's the probability a randomly selected person has at least 1 pet? Well, that's basically going to be all these, right? I'm going to add up these probabilities. Or I can think about it as 1 minus the probability of no pet raised to the nth power. Well, it's just one person. So the probability of not having a pet is 0.4 and raised to the first power. Well, that's 0.6. So there's a 0.6 probability that a random person is going to have at least 1 pet. And again, I could have added those 3 probabilities. I would have gotten 0.6 also. So now, out of 4 people, what's the probability at least one of them has a pet? So I'm going to think of this as a tree, okay? So I got my first person. They either have a pet or they do not. So they either have a pet or they do not, okay? Second person, pet or not. All right, pet. Pet or not. So 0.6, 0.4. So I could do this 4 more times, okay? But I'm not going to because trees start to get very crazy after like 3, okay? But if I think about my probability here, 1 minus the probability of no pet raised to the nth power, my n is my 4 people, okay? My probability of no pet was 0.4, so now I'm going to raise that to the 4th power. Because again, down this branch of no, no, and no, this is the only branch where there is nobody that has a pet. Every other branch in the tree is going to have at least 1 person that has a pet. So if I take all these probabilities that add up to be 1 and subtract that one, I will have the probability that at least 1 person has a pet. Okay? I don't even know what this answer is. It is 0.9744. Okay, very high probability that at least 1 person out of 4 is going to have a pet, given that there's a 0.6% chance that you have a pet. Okay, but that's you can think through the tree without actually writing the whole tree. Okay, every single branch has at least somebody that has a pet, except for that last one. So that's why we take 1, which is the total of all the probabilities, and subtract that last not branch. Okay, 0.4 to the 4th power, 1, 2, 3, 4. Okay, all right, let's do a couple quick examples. All right, if the probability of San Francisco having an earthquake with a rating of 7.5 or greater on the Richter scale is 0.02, that's a pretty major earthquake, guys. What's the probability that San Francisco will have at least 1 major earthquake over the next 10 years, 25 years, and 5 years? Okay, so if I follow my 1 minus the probability of none raised to the nth power, all I have to do is think about what's the probability of not having an earthquake. Well, if the probability of having an earthquake is 0.02, the probability of not having an earthquake is 0.98. So I would do 1 minus 0.98 to the 10th power, because that's 1 minus the probability of not having an earthquake to the 10th power. 1 minus 0.98 to the 25th power for 25 years, and 1 minus 0.98 to the 5th power for 5 years. Okay, so if we calculate these out, let's look at these. Okay, think about it. What's the probability that San Francisco will have at least 1 major earthquake over the next 5 years? Very short time span. Not too high, like 10%. Over the next 10 years, starting to get up there, because probably within a 10-year span, they may have an earthquake. 25 years, probability gets much higher, okay? So within 25 years, the probability that they're going to have at least 1 major earthquake is pretty significant, 40%, okay? Now, again, this is our application of the 1 minus probability of none to the nth power for at least 1. Now, I want to compare these to the probability of a major earthquake every year over the next 5 years. So if we think about that, again, in terms of a tree, year 1, earthquake, no earthquake. Okay, so earthquake, no earthquake. Okay, year 2, earthquake, no earthquake. Earthquake, no earthquake. The probability of a major earthquake every year over 5 years is this earthquake, this branch, up 5 times. 1, 2, 3, 4, 5. So this would be 0.02 to the 5th power. And 0.02 to the 5th power is 3.2 times 10 to the negative 9, which is essentially 8 zeros. Okay, which is essentially 0. San Francisco is not going to have a major earthquake every single year over the next 5 years. Okay, so this branch usually is not going to happen. Okay, but this is a very different, and again, you can still get it from the tree. This is a very different scenario than the at least one. At least one over the next 5 years, that would be the branch where it's like earthquake and then no, 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 no. Or no earthquake, no, no, no. Okay, so you're going to have at least one. If we did this in 5 branches, all these branches would have at least one earthquake, except that bottom one where it had the 5 no earthquakes. Okay? Okay, anyway. That's my explanation of the 1 minus the probability of none to the nth power as our shortcut for my at least 1 probabilities. And we will see at least 1 again in chapter 6 when we start talking about binomial distributions. Okay, I hope this was helpful, and I will see you guys later.